Good, so welcome to another masterclass, and today we're working on A2 level chemistry. This is a past paper from the summer series in 2015. What we're going to do today is, because this paper actually is a 2-hour paper, and we've only got maybe an hour, hour and a half on the masterclass, there isn't time to go into depth of every single question. So what I'm going to do, I'm going to pick particular questions that the examiner has picked up that students have the most difficulty with. Other questions, it's fairly easy for you to check in the mark scheme, but there's particular questions the examiner felt that students needed particular attention to. So rather than trying to do everything, which we can't do, it's a 2-hour paper, we'll just focus on those questions where the students had the most difficulty. And actually, we start off with question number 1. And these electron configurations, they're pretty easy. You can look those up either in a textbook or a mark scheme, work out the formula. You can draw dot cross diagrams. That's all covered in the mark scheme. But it's when you get down to a question part C at the bottom that the students are having more problems. So that's where we're going to launch in to this paper today. And it says you have to look up these standard cell potentials in the data booklet. And when you do that, you find that for fluorine, if you look that up in the data book, then you have this equilibrium. Trying to get that to work. There's 2 electrons making 2 fluoride ions. And if you look up the standard cell potential in the data book, then you get 2.87 volts. And if you look up chlorine, then this is a standard cell potential as well, 2 chloride ions, and you have plus 1.63 volts. All right. Now, the trick with all of these kind of questions is that this value here is an electrode potential. So these are all about how positive an electrode is. And if you compare these 2 electrodes, you can see that this one is more positive than this one. So if you're comparing these 2, then electrons, which are negative, are going to go to this electrode much more than they are to this one. This is the most positive standard electrode potential. So if you compare those 2, this reduction is going to happen much more easily than this. And if that reduction is happening, then you can see that's written as a reduction. These standard electrode potentials are always written as a reduction. If that reduction is happening more easily than that, that means that fluorine is oxidizing something more easily than chlorine. So fluorine is the stronger oxidizing agent. And if you continue down the halogen group, then chlorine would be more strongly oxidizing than bromine, which would be more strongly oxidizing than iodine. Now, you've got to use that kind of information here, because as you go down the halogens, if you go up to the top of the halogen group, they're more oxidizing. Yes? Because fluorine is more oxidizing than chlorine, chlorine is more oxidizing than bromine, bromine is more oxidizing than iodine. And the inverse applies then for the ions. Here you've got bromide ion, iodide ion, chloride ion, fluoride ion. So the fluorine molecule is most oxidizing, but the iodide ion is most reducing. So you've got that pattern in group 7 for the diatomic molecules here and for the anions over here. Fluorine is most oxidizing and the iodide ion is most reducing. And then you've got to predict the type of reaction that would happen between this interhalogen compound and potassium bromide, well, we've said that the bromide is most reducing. Okay, so you've got a bromide ion here. There's going to be a reduction that's going on here. So the type of reaction is going to be reduction and oxidation happening together. It's a redox reaction. And you've got to construct an equation for that reaction. Well, you've got the bromide ion, and we know from up here that it's reducing, which means itself is going to be oxidized, isn't it? Okay, so you can see there the oxidation number is going up. Bromide ion is being oxidized to bromine. And then you've got these two here. And because the bromide ion is most reducing, then these two are going to be reduced, aren't they? So if we reduce chlorine from there, you're going to get chloride. And if we reduce fluorine from there, you're going to get fluoride. So the overall reaction is that. Or if you wanted to put the potassium in, you could have the interhalogen compound there, plus 2. Potassium bromide is going to potassium chloride, plus potassium fluoride, plus bromide. And that reaction all happened because the bromide ion, compared to the fluoride and the chloride, was the most reducing. And you can see here that chlorine has been reduced to chloride, the fluorine has been reduced to fluoride, and the bromide, because it was the reducing agent, has been oxidized up to a bromine molecule. Okay, now the examiner and the mark scheme generally found that question 2 was quite well done. We're going to skip that because we're quite short of time, and we're going to skip as well question 3. So scrolling right along here, and we're going to drop into one of the harder questions, question 4. So we're moving quickly through here. Okay, where's question 4? All right, so this question starts by asking about the solubility product of silver sulfate. Now, what's going on here is that here's silver sulfate, and if we dissolve it in water, or try to dissolve it in water, it's not very soluble, then we get 2 silver ions, don't we? And we get 1 sulfate ion. And you can see that an equilibrium has been set up here, can't you? So for any equilibrium, you should be able to write an equilibrium expression for the equilibrium constant, Kc. So Kc is equal to the silver ion concentration, and we've got 2 of those, so I'll put a square there, and the sulfate ion concentration. And that's all over this, the original silver sulfate. Now, the trick at this point is to notice that this substance, the silver sulfate, is solid, and only a little bit is it dissolving up. But the concentration of a solid doesn't change. It's only the concentration of the ions in solution that change. So the concentration of a solid is always constant. And because the concentration of the solid is constant, we can just include it in the equilibrium constant. And when you include the concentration of the solid in the equilibrium constant, then instead of calling that Kc, it's called the solubility product. And the solubility product just shows that we've included the concentration of the solid in the equilibrium constant, because the concentration of the solid itself is a constant. So this expression here is the correct expression for the solubility product. And strictly speaking, you should put in the state symbols in there to show that you're talking about ions in solution, because we've incorporated the solid into the solubility product as the constant over there. So the correct expression for the solubility product is the silver ion concentration, and we have the state symbol in there, and we have two of those, and we've got the sulfate ion concentration there. Now, that's our solubility product expression, and these concentrations, of course, are in moles per decimeter cubed. So you've got moles per decimeter cubed here, but that's squared, isn't it? And you've got moles per decimeter cubed here, and you're multiplying those together. So you've got moles squared times mole, so that gives us mole to the cubed, and you've got decimeter cubed squared times decimeter cubed, which is decimeters to the -9. All right, now this next step here is we've got to calculate, haven't we, the value for the solubility product of silver sulfate. Now, you can see here that, okay, so here's the silver sulfate, and the concentration is of that's dissolved is 2.5 moles per decimeter cubed of silver sulfate. So that would mean there is 2.5 times 10 to the -2 moles per decimeter cubed of the sulfate. But for the silver ion concentration, because you've got 2 moles of silver ion for every mole of sulfate ion, there's 2 times 2.5 times 10 to the -2, because there's twice as much silver ion in solution. So those are your concentrations, and the solubility product is that concentration times that concentration. But you can see in the solubility product that that concentration is concentration squared. So you've got to have 2 times 2.5 times 10 to the -2 squared times 2.5 times 10 to the -2. And if you work all that out, you end up with a result of 6.25 times 10 to the -5, and it's in these units up here. And because the values up here were given to 2 significant figures, you're going to express this to 2 significant figures as well, which is 6.3 times 10 to the -5. And just so you're absolutely clear to the examiner, you can write 2 significant figures after that. Good. So now they're continuing to talk about silver sulfate, and you've got to label up this little energy cycle here. So this is the solid, and over here, this is going to be the solid dissolved in solution. And remember, that is 2 of the silver ions and 1 of the sulfate ions, and we must have state symbols in here like that. And that change is the enthalpy of, or the standard enthalpy of solution, which I think was one of the ones they wanted you to give, wasn't it? This one up here. Okay, so that's the enthalpy change of solution. This one down here, you can take the ions in the gas phase. That's why it's important to put in the state symbols, and the sulfate ion in the gas phase. And that, when you're converting the ions in the gas phase to they're fully hydrated here in solution, that's the standard enthalpy of hydration, isn't it? Now, this one over here, if you wanted to break the lattice and convert the solid into the gaseous ions, that would be the enthalpy of lattice dissociation. But here you're actually forming the lattice from the ions in the gaseous phase. So this is the enthalpy, or the lattice enthalpy for this one. And we've got our arrows marked there and marked there. So we've marked up everything that was required for that little Hess's law cycle. So that's been relatively tame so far. And now it's time to make life a bit harder for you. So they've now taken all your thinking about silver sulfate and the fact that it is only sparingly soluble, only a little bit of this silver sulfate is soluble, and you can see there's some solid silver sulfate at the bottom of this beaker here. And then you've got a new set of reagents on the left-hand side over here. So you've got to calculate from values in the data booklet, which will be electrode potentials. You've got to work out the cell potential here. And if you look those up in the data book, then for the left-hand side of the cell, you've got this, haven't you? And these these electrode potentials are always written as reductions, aren't they? You can see the iron 3+ is being reduced to the iron 2+. And the electrode potential for that in the data book is 0.77 volts. And then on this side, you've got a silver electrode, and you've got silver ions in solution. And so the equilibrium that's set up, again, is a reduction. And you can see there that this silver ion is being reduced to silver metal. And the data book gives us 0.8 volts. All right, so you've got to work out the, from these electrode potentials, you've got to work out the cell potential. And the way to do this is to look at these and work out which one is the most positive. Well, they're quite close together, aren't they? But the this one here, the reduction of the silver ion, is the most positive. So that's the most positive, and that's the least positive, you could say, or the most negative. And at the negative electrode, there's going to be electrons being lost because they're pushed away from the negative electrode. But at the positive electrode, the electrons are going to be gained. And if you've got electrons being lost, oxidation is loss and reduction is gain. So if you think about these different systems as the most positive and the most negative electrodes, the most negative electrode will push electrons away, electrons are lost. The most positive electrode will gain electrons, and you have the reduction that's happening there. So when you look at these two equations up here, then the one that's going to be a reduction is going to be that one, and the one that's going to be an oxidation is going to be that one. But these are both written as reductions. So we have to change this one to make it be an oxidation rather than a reduction. So we swap that around, and you have Fe2 plus is going to Fe3 plus an electron. And because we've changed the direction of that, the electrode potential now is 0.77 volts. So we've changed the direction of that reaction there. And then we can now add that equation and that equation together. And if we add them together, then we get a cell potential there of, what is it, plus 0.03 volts. So the cell potential is 0.03 volts. And it's very important that you put positive or negative sign in front of that. And we worked out, didn't we, that if you compare these two electrodes, which one is the most positive? Well, that one is the most positive. The most positive electrode is the silver iron, silver solid electrode. Now, this question here was one that the examiner felt that students had a lot of difficulty with. Now, these standard cell potentials assume that you've got 1 mole per decimeter cubed is your standard concentration for the standard cell potentials. But you know from the earlier work you did in the question that actually it's very, very difficult, it's impossible to get a standard solution of 1 mole per decimeter cubed silver ions, because the silver sulfate is only very, very sparingly soluble. So under real conditions, not standard conditions, the silver ion concentration is much, much less. And so you've got to think like this, that over here, the equilibrium is this, isn't it? That's the equilibrium that's being set up. Now, if our silver ion concentration is going down, because it's less than 1 mole per decimeter cubed, then if the silver ion concentration goes down, this equilibrium is going to be moving to the left. The position of equilibrium is going to be moving to the left. So the position of equilibrium moves towards the reactants. And if the position of the equilibrium moves towards the reactants, then more electrons are being produced, aren't they? Can you see that if this equilibrium shifts to the left, then with more electrons being produced. And if more electrons are being produced and left on that electrode there, electrons are negative, so that electrode is going to be becoming less positive. So the electrode is becoming less positive. Now, if the electrode is becoming less positive, then the difference between these two here is less, and so we'd expect the cell potential to become even less as well. So the cell potential is less positive also. And to work all that out, we had to remember that we were working with an equilibrium. And as the silver ion concentration decreased, the equilibrium shifted to the left, which meant more electrons, which have negative charges, get left on the electrode. And so the electrode becomes less positive, and so the cell potential as well becomes less positive. Okay, so coming on to this next section here, we're adding a few drops of concentrated sodium sulfate, which is completely dissolved in solution. Now, on the left-hand side here, the equilibrium is this one, isn't it? We've got an equilibrium between the iron 3+ and the iron 2+ ion. So when we add the sulfate ion, it has no effect on this equilibrium between the iron 3+ and the iron 2+. Sulfate isn't involved in that equilibrium at all. So we expect for this electrode there to be no change. But when we add the sulfate, here it is, to the beaker on the right-hand side, over here, then what's going to happen is the silver ion, when we increase the sulfate ion concentration, remember there's an equilibrium to form solid silver sulfate. As we increase the sulfate ion concentration, this equilibrium is going to shift towards the right-hand side. And so we just need to follow exactly the same logic as we had before, that what's happening is that the silver ion concentration is being decreased as far as the electrode is concerned. Remember, the electrode reaction is this, isn't it? That equilibrium. So if we decrease the silver ion concentration, the position of equilibrium shifts to the left. And that means that more electrons are left on the electrode. You can see if we shift this equilibrium to the left, there's more electrons. If there's more electrons left on the electrode is less positive because there's more electrons on there. And if the electrode is less positive, then the cell potential itself is less positive. Because if you go back up here, you can see that if the electrode potential is less positive, then overall the cell potential will be less positive as well. Good. All right. So you just had to remember that when you're dealing with these electrode potentials, you're dealing with an equilibrium. And if we reduce the silver ion concentration by adding sodium sulfate, this electrode equilibrium here shifts to the left. Good. All right. So for the next one here, it's now focusing on the iron. And it's saying, well, the iron ionizes in solution to produce hydrogen ions. It's acting a bit like an acid. It's producing hydrogen ions. And so you've got to treat this in a little bit like the way you've learned to deal with pH calculations for acids that you're much more familiar with. But here you've just got this ion complex, which is giving you this H+ ion in solution, so it's acting as an acid. And what you've got to remember is that this dissociation constant for this process here is very, very small. So when that process happens, because the dissociation constant is small, only a tiny amount of that and a tiny amount of that is formed. So the concentration of this is relatively unchanged. So if you had to write the equilibrium equation for this, you'd have this ion over here, you've got all that, the concentration of that, and you've got the concentration of the hydrogen ion over the concentration of this ion here. Now, what you have to spot is, of course, that the concentration of that and the concentration of that are actually the same, because you've got one hydrogen ion there and one of these ion complexes here. So a different way of writing that is to say, well, these two concentrations are the same, and so what we can say is, because they're the same, you could write in there the hydrogen ion concentration, because the hydrogen ion concentration and the ion complex concentration are the same. Those two are the same. So it's just to make that even simpler, because you multiply those two together, you've got that. Now, remember that the acid dissociation constant is very, very small, so only a tiny amount of this product is formed. Most of it is still in the reactant. And so you can say that this reactant concentration has hardly changed. So it's an approximation to say, I have that as an approximation, that this concentration actually is hardly changed at all at the point of the equilibrium. So the concentration there was 0.1, wasn't it? Okay, so you've got the acid dissociation constant is approximately equal to the hydrogen ion concentration divided by the original concentration of the ion complex over here. But the little trick that they're trying to play on you here is that you started off with this iron compound here, and when it dissolves in solution, it's actually making two of those. So the concentration isn't 0.1, because that was the concentration of this iron sulfate, which contains two iron ions, and so the concentration of iron complex in solution is 0.2. So you ended up with a calculation here where the acid dissociation constant is approximately equal to the hydrogen ion concentration divided by 0.2. So now you've got to multiply that up, and then you end up with 0.2 times Ka is equal to the hydrogen ion concentration squared, or if I rearrange that to make the hydrogen ion the subject to the equation, that's the same as saying the hydrogen ion concentration is 0.2 times the acid dissociation constant. So you've then got to plug in these numbers here. 0.2 you've got the acid dissociation constant up there. You're going to take the square root. That'll give you the hydrogen ion concentration, and then you've got to say that the pH is the negative logarithm to the base 10 of the hydrogen ion concentration that you calculated here. And if you work through all of that, you end up with a result of 1.87 for the pH, because you've taken the negative logarithm to the base 10 of the hydrogen ion concentration that you worked out here. Okay, good. So we're now going to actually move on to question 5, because that was another one that the examiner felt that students had a lot of difficulty with. This part of the equation, the question, was actually quite easy. You could just work out protons, electrons, and neutrons for that. You look that up in the mark scheme. That's relatively easy to do. Now, this next section here is all about the relative reaction of group 14 chlorides. Okay, so you've got, if you look down group 14, you've got carbon, silicon, and then germanium, and then you've got tin down here. These are all group 14 chlorides. And you've got to talk about their reaction, haven't you, with water, I think. Yes, sorry, the reaction with water. Okay, all right. So with this one, there's no reaction. We'll come on to why in a moment. So there's no reaction there. For this one, you'd expect to see steamy fumes. And the reason for that is because you are reacting it with water to produce hydrogen chloride gas. Okay, and you've got 4 chlorines there. You can have 4 of that. There's 2 of them. What am I talking about? Okay, so it's plus 2 H2O, isn't it? Let's just check that balances. So you've got 4 hydrogens here, 4 hydrogens here, 4 chlorines, 1 germanium, and you've got 2 oxygens. Yes, that all balances up. And this is exactly the same, and this is what's the steamy fumes of the hydrogen chloride gas that's produced, and you get exactly the same kind of thing happening here. And you've got the reaction of tin chloride plus 2H2O is going to steamy fumes, the hydrogen chloride, and then you've got the same reaction going on there. Now, you've got to give an explanation of the difference in these reactivities. Now, there was no reaction up there, but here you got a definite reaction. You're getting these steamy fumes of hydrogen chloride because the group 14 chloride is reacting with water. And there's the reasons you have to give for that is carbon, if you look it up in the periodic table, is in group 2. Germanium is in group, sorry, what do I mean? I mean not group 2, I mean period 2. So carbon is in period 2. Germanium, if you look it up, is in period 4, and tin is in period 5. And so in period 2, the electron configuration for carbon is 1s2, 2s2, 2p4, and there's no, in period 2, no d orbitals in period 2. But in period 4 and in period 5, there are d orbitals. There are d orbitals. And so if we look at this reaction of these group 14 chlorides, then there's going to be the chloride ions will be slightly negative, and the central ion there is going to be slightly positive because these are more electronegative, which means that the water molecule here, which has its lone pair of electrons, is going to be attracted, because that's a slightly negative end of the water molecule, that's a slightly positive end of the water molecule. That water molecule is going to be attracted in to attack the central atom of these group 14 chlorides. And so that is nucleophilic attack. And as that lone pair of electrons reacts with that central atom there, then if it was if it was carbon in the middle there, there's no d orbitals to accept the lone pair of electrons. But for germanium and for tin, there are d orbitals to accept the lone pair of electrons, and so the water molecule can get into the center there, and the lone pair of electrons can be accepted by the available d orbitals, and a reaction can happen. And so the reason for the difference in reactivities is there are available d orbitals in germanium, which is period 4, and in tin, which is in period 5. The other reason that isn't important here, but you could include in maybe another question, is that if that atom was carbon, then compared to carbon, chlorine is a much bulkier, a much bigger atom. So in addition to there being no available d orbitals, then the water molecule can't actually fit in the first place to do its nucleophilic attack, because it is blocked by the bulky chlorine atoms around the outside. And so there's an additional reason of steric hindrance. That means the difficulty of a small molecule getting in between large chlorine atoms there. But the key point that they're asking you to get here is that there are available d orbitals in germanium and available d orbitals in tin, but no available d orbitals in carbon because it's in period 2. All right, so you've now got to look at a reaction between tin chloride and chlorine, and lead chloride and chlorine. And if you look those up in the data book, you have, of course, these are written as reductions, aren't they? So that's written as that reduction. And the chlorine is written as a reduction as well. and the electropotential for that was 0.15, and the electropotential for the chlorine was 1.36. So if you compare those two, which is the most positive electropotential, well, it's clearly that one. So that's the most positive, or that's the most negative. And if this is the most positive, then electrons will go to that. So that'll be electron gain. And this is negative, we'll be pushing electrons away. That'll be electron loss. And oxidation is loss of electrons. Reduction is gain of electrons. So if you compare these two, then this one is loss of electrons, so you'd need to write that the other way around, which is and if you add those two electropotentials together, you get plus 1.21 volts, don't you? So that's that redox reaction, that reduction there, and that oxidation there, that actually works because you get a positive electropotential here, 1.21 volts. So for that, chlorine can oxidize tin 2+. Now, if you work through the same kind of reasoning for lead, then you'd have lead 4+ plus 2 electrons going to lead 2+, and this time the standard electropotential is 1.69, and this time this is the more positive, not the chlorine. So for this occasion, the chlorine cannot oxidize the lead 2+. So that reaction will run, but the equivalent reaction there will not run. So chlorine can oxidize the tin 2+, the chlorine cannot oxidize the lead 2+. Okay, next one. So the Faraday constant and the Avogadro constant. So the point about the Avogadro constant, it allows us to move between the tiny things that happen at the molecular level and the kind of things that we can actually measure in the lab. So it's a multiplication that allows us to multiply up to actually things that we can measure. And the Faraday constant is, all that is the charge on the electron, which is tiny, just really, really tiny charge, times a very, very large number, which is 6.02 times 10 to the 23. So we can say that the Faraday constant is just the charge on one electron multiplied up by a mole of electrons. So that's the charge carried by 1 mole of electrons. And so the relationship is that the Faraday constant is equal to the Avogadro constant times the charge on one single electron. And so that gives us the total amount of charge on 1 mole of electrons. So that's the relationship there. That the Faraday constant is equal to the charge on one electron multiplied by the number of electrons in a mole. And then this calculation here, they very kindly talk you through it as well. So you've got to do how many? You've got to do 5 steps there. 1, 2, 3, 4, 5. Okay, so first of all, you've got to calculate the amount of oxygen produced. Well, it says that there was 130 centimeters cubed of oxygen. So you know that the amount of moles is equal to the volume divided by the molar volume. That's a little bit like saying the number of moles is equal to the mass divided by the molar mass. And so the number of moles of oxygen is equal to the volume of oxygen, which is 130 centimeters cubed, but we need to be consistent with units here. So that's 0.13 decimeters cubed divided by the molar volume, which is 22.4. Oh, sorry, at standard, at room temperature is 24 decimeters cubed. And that gives you, my calculation, the number of moles of oxygen is 5.416 times 10 to the minus 3. That's the moles of oxygen. So that's number one done there. Number two is the number of moles of electrons. And so we just look at the stoichiometry here. For each mole of oxygen, there are 4 moles of electrons. So the amount, or the number of moles of electrons, is just 4 times the amount, or the number of moles of oxygen, which comes to 2.17 times 10 to the minus 2 moles of electrons. So we've done number 2 there. Okay. Now, this next one, the number of coulombs passed. Okay, that one there. So 1 coulomb is the amount of charge when you've got 1 amp that passes a point in 1 second. Now, you didn't do this for 1 amp for 1 second. Instead, you did not 1 amp for 1 second, but you did 1.2 amps for, well, not, so we've got to work out seconds here, haven't we? So the number of coulombs is equal to 1.2 amps times the number of seconds. So, well, that was 30 minutes times 60 to give us the number of seconds. And that, if you multiply that up, that gives us 2,160 coulombs. So that's number 3 there. So we've got, that is the number of moles of oxygen, that's the number of moles of electrons, and that is the amount of charge. So 1.2 amps for 30 minutes times 60 seconds. Next one, so that was our, we did 1 there, 2 there, 3 there. 4 is the number of electrons passed. Well, if you look up in the data book, the charge on an electron is absolutely tiny. The charge on an electron is 1.6 times 10 to the minus 19 coulombs. Okay, tiny, tiny charge. But so if you had that many coulombs and the charge on each electron is that tiny number, 1.6 times 10 to the minus 19, then the number of electrons, which is what they're asking us to calculate, must be that divided by this tiny number here. So you've got that number of coulombs divided by that charge on each electron, 1.6 times 10 to the minus 19, and you're dividing coulombs by coulombs, you're just going to get a number there, and you end up with a result of 1.35 times 10 to the 22. As it's just a number, isn't it? Okay. So during that 30 minutes, just a huge number of electrons traveled down the wire. That number. And so you've got the number of electrons, and you've got the amount of electrons. So you've got 2.17 times 10 to the minus 3 moles is equivalent to 1.35 times 10 to the 22. That's the number of electrons. But you're wanting to work out, so that was our number 4 there. So we've worked out the number of electrons. We want to work out the number of electrons in 1 mole. So we've got here the number of electrons not in 1 mole, but in that many moles. So to get 1 mole, we just say, well, for 1 mole, we must have that many electrons divided by that many moles. And if you do that calculation, then you end up with a result of 6.2 times 10 to the 23. And because you've taken a number there and you divided it by a mole there, the unit is mole to the -1 because you've taken a number and divided it by a mole. And so this is, if you like, the classic way in a laboratory in which you estimate a value for the Avogadro constant. Now, the examiner said that if you just guessed, because you knew that the Avogadro constant was 6.022 times 10 to the 23, like you might know that. If you just guessed that value and put it in at the end of the calculation, you'd get no marks. They're asking you to do this calculation, and through experimental error, you've got a value of 6.2 times 10 to the 23, which is pretty close to the value that we know, which is 6.02 times 10 to the 23. So the examiner is giving you the marks to get that value down there. And so this sort of stepwise calculation of doing electrolysis, measuring the amps that pass over a certain amount of time and the amount of oxygen that's produced allows you to do this kind of calculation, and you work out an estimate for the number of electrons in a mole, which is the same as the Avogadro constant. Okay, so I think in my plan I'm now skipping question 6. I think that's all fairly obvious if you look that up in the mark scheme. And I'm going to go on to question 7. Let's see if I can scroll up to there. So this is all question 7. All right, okay, so talking about cracking here. So you've got a cracking reaction. And when you take hydrocarbon over here and an alkane, you get long chain alkanes from fractional distillation, and you want to crack them. And when you crack them, you get a shorter chain alkane and alkenes. Now, if you look at these, well, which one is the alkene and which is the alkane? If you know your homologous series, then the general formula for an alkene is that, and the general formula for an alkane is that, CnH2n plus 2. So that's the alkane there. So if you look at these, well, that must be the alkane, because you've got a general formula of Cn equals H2n plus 2, and this one over here must be the alkene, excuse my writing, because you've got CnH2n, which is that there. So these isomers are alkenes, and this one here is an alkane. And the conditions here for cracking are, you can look that up, and you need a catalyst, typically, say, aluminium oxide. So you know, because this is an alkane, then you can do a structure for the alkane over here. Structure for the alkane, they haven't asked whether you meant to draw a skeletal formula or a structural formula. I think you should be drawing, we can draw a displayed formula to be absolutely crystal clear. This is an alkane, 3-carbon alkane. You're looking at C3, 1, 2, 3, H8, 1, 2, 3, 4, 5, 6, 7, 8. So that is the displayed formula for that alkane. Now, these over here are going to be alkenes, aren't they? C, D, and E, they're all alkenes. And so you've got to suggest some structure for the 3 different alkenes that can be formed. So for me, I'm just going to try and rattle through this here. So the possible structures are, well, you could get, I'm not drawing hydrogens at the moment. You've got, what, they 5 carbons long. So it's, let me try and draw that a little bit more neatly. So you've got, is that 5 carbons? 1, 2, 3, 4, 5. Now I haven't drawn the hydrogens in at the moment, just for sake of clarity. And then you could move the double bond from this position here to the second position there. So you'd end up with that. And then if you moved it along to another position here, it'll just be the same as this. So the actual other isomer is going to be the geometrical isomer of that. So just, excuse me, I'm not drawing in the hydrogens. So you've got that. Now, and then you can draw in the hydrogens here, just to be completely clear. But I personally, just for the moment, for the sake of doing this question, I'm just going to leave the hydrogens out so we can see quite clearly what's going on. Okay, so those are the three possible isomers that we had, because we knew that those were all alkenes, and so it's got to be a double bond in there somewhere. Once you draw them out, those are the only possibilities for the isomers. And then you're reacting it, aren't you, with this concentrated oxidizing agent. So you're heating with a concentrated oxidizing agent. And when you do that, we'll just do this one here to begin with. It's a little bit easier to understand. So when you take the hot concentrated oxidizing agent, you're going to do an oxidation that's happening here, and the double bond ends up giving you a ketone at the end there and a ketone at the end there. So you end up with, I'm just drawing carbons again at the moment. So you get that, and similarly over here. No, sorry, I don't mean a ketone. I mean an aldehyde that's forming here. If I drew in the hydrogens, this would be an aldehyde here, and this has similar products over here, an aldehyde here, and an aldehyde here. So that's the first step of the oxidation. But you need to remember that because you've got this oxidizing agent here, the first step is that you produce this carbonyl group here, which is an aldehyde. But then aldehyde can do a subsequent oxidation to a carboxylic acid. So that's going to give us that carboxylic acid and that carboxylic acid. And you get the same over here. You've got that carboxylic acid, and you've got that carboxylic acid over there. So I'm just going to rub out the carbonyl, or the aldehydes that were an intermediate, if you like, on the way to forming those carboxylic acids. And so the products here are ethanoic acid. I haven't drawn in the hydrogens. And over here, propanoic acid. Ethanoic acid, propanoic acid over here. Now what happens over here is you're going to get, again, I'm not drawing in the hydrogens, you're going to get the carbonyl compound, and over here, when this oxidizes up, you're going to get carbon dioxide. It's full oxidation of that carbon atom there. And then because you've got this butanal here, it'll go further in its oxidation from butanal up to butanoic acid. So you're going to get further oxidation to give you butanoic acid. Because the butanal underwent further oxidation to give you butanoic acid. And so you've got carbon dioxide and butanoic acid, ethanoic acid, propanoic acid, ethanoic acid, propanoic acid. And because you're being asked for structures here, then I think the mark scheme probably draws a skeletal formula here. I haven't checked the mark scheme. So this was question 7. Oh, so the mark scheme is giving you not skeletal formulas or displayed formulas, but structural formulas. So you've got to put in at each of these stages here these structural formulas rather than these fully displayed formulas or the skeletal formulas. So that means this one in here, you're going to be writing H2C, and then you're writing well, you'd be writing this, sorry. You'd be writing CH2, which is that one there, then CH for that one there, and then you'd be writing CH2, CH2, CH3. So that's the structural formula for that. I just found it easier to write out these carbon skeletons here. And for this one here, you've got CH3, haven't you? Then you've got CH, then you've got CH, and then you've got CH2, and you've got CH3. Well, strangely enough, the mark scheme gives the structural formula, but it's asking to know that this is on the same side here, so that's cis, and this one here is trans. So you've got to mark these up as cis and trans isomers. So that they're the same formula there. But one is trans and one is cis. And then down here you had carbon dioxide and butanoic acid, and over here you had ethanoic acid, and you had propanoic acid, ethanoic acid, propanoic acid, and you had to write out the structural formula for each of those. And you, when you did these ones up here, you had cis and trans. The other way of expressing those is on this one, they were on the same side, so those are Z isomers, and these are on opposite sides, so they are E isomers. And the type of isomerism that's there is a special type of stereoisomerism, which is called geometric isomerism. So technically, I think the right answer there is geometric isomerism. If you said cis-trans isomerism, you got the mark, or if you said the ZE type of isomerism, you got the mark as well. Okay, so this reaction here, you've got propene, you've got the double bond reacting with bromine. That's a strange question there. Normally you would carry that out in the dark because you don't want the bromine molecule to have a homolytic fission, which you know is the reaction that you have if you carry out the bromination with alkanes. So you're just running that reaction in the dark. Now the type of reaction that's happening here is you're adding the bromine molecule across that double bond. So because you're adding it, it's an addition, isn't it? And because that's very electron rich, you've got a very an area of high electron density, then species that are attracted to areas of high electron density will start to react with that. So they need to be electrophiles that are attracted to that. So that's electrophilic addition. Now, in all the examiner's comments, the examiners are always saying that students find drawing mechanisms a weak point, and that's one of the discriminators between A-star students and other students who aren't at the A-star level, is their ability to accurately draw mechanisms. So we'll just go through this very, very carefully. So you've got, what was it, propene. The methyl group, and that's bonded to this double bond here. The bromine molecule approaches, we have high electron density here. Causes this bromine molecule to be polarized. All the electrons in the bromine molecule get pushed down here, so that's a slightly negative charge, and you've got a slightly positive end to the bromine molecule here. And so you've got this temporary dipole, or this infused dipole created, and that means you get a bond pair of electrons from the double bond going to the bromine molecule there. And you've got to show that bond pair of electrons moving there, and you've got to show that bond pair of electrons moving there. And so you end up with this. Now it's very important that you draw it this way around. Because the bond pair of electrons has moved away, we've ended up with a positive charge there, and a negatively charged bromide ion there. Now the reason that's important is that you've drawn here a carbocation with the positive charge on a carbon that is attached to two methyl groups. So that's a more stable carbocation than if you'd drawn it round the other way. So if you'd drawn this, you could have drawn it round that way, that's equivalent. But yeah, that could be an intermediate as well. And this is a primary carbocation, and this is a secondary carbocation. And the secondary carbocation is more stable than the primary carbocation. So this one is preferentially formed, it's more stable because you've got electron releasing groups there and there, which reduce the charge density on the carbocation carbon there. So that positive charge is reduced in the secondary carbocation, but over here, you've only got one electron releasing group. And so that carbocation in the primary carbocation isn't reduced, the positive charge is not reduced here as much as it is here. So this is the correct intermediate, and that's the incorrect intermediate. You should be showing this as the correct intermediate. And once you've got that correct intermediate, the secondary carbocation, then the next stage of the reaction is that the lone pair of electrons on the bromide ion form a bond by forming a bond pair with the carbocation here. And so you've got now that forming there. So they were only giving you 2 marks in this, but it's very, very important that you had the correct carbocation intermediate as the secondary carbocation and not the primary carbocation. And you very carefully showed that you had this dipole forming on the bromine molecule. You got a movement of a bond pair of electrons there, a bond pair of electrons there, and then this lone pair of electrons moving in to form a new bond pair of electrons between the carbocation and the bromide anion. Okay, so let me see, which question am I trying to focus on here? So we've looked through question 8. I'm not going to go through that. That seems pretty straightforward when you look at the mark scheme. I wanted to look at question 9. Did I? Let me see. No, I didn't. Oh, yes, I did. Sorry. Okay, question 9. All of this part of question 9 about DNA fingerprinting, that's all pretty easy to understand from the mark scheme. What I wanted to focus on was all this work on partition coefficients. because there's a bit of a calculation you've got to do there. It's not a very common question to work on the partition coefficients. So let's just talk about the partition coefficients a little bit to finish off this paper. So partition coefficients, where you normally encounter that is where you've got, say, a solution of something in water, and you mix it with another solvent. Now, the other solvent they talk about down here is hexane. So you've got a solution of something in water, you could just say aqueous, and you are mixing it with another solvent, and some of that solute goes and dissolves in the hexane. So typically when you see this, you might have got some kind of flask set up, and you've got two solvents, one of which is hexane. It's the least dense, so it probably floats on top there, and this is the water. It's more dense, it's down the bottom here, and you've got some substance X, we don't know what that is, and some of it can dissolve in the hexane and some of it can dissolve in the water. And what's happening is all the time is the molecules or the particles of X are in dynamic equilibrium with the particles of X in the water. So you've got this dynamic equilibrium set up. You've got particles of X, some of which are dissolved in water, some of which are dissolved in hexane, and they're constantly moving between those two immiscible phases. You've got a hexane phase and a water phase. And the partition coefficient is just the equilibrium constant for the movement of the solute between those two phases. So the partition coefficient is then the concentration in this phase over here, which is X in the hexane phase, over the concentration of X in the water phase. Okay? That's what the partition coefficient is. And so it's just the ratio of the concentration in one phase compared to the concentration in the other phase. So it's the ratio of solute concentration in two phases of immiscible liquids. And because the hexane and the water are immiscible, we saw that there's an equilibrium set up. The partition coefficient is just the equilibrium constant of the concentration of the solute in the two different phases. So that's what you're trying to say there. And the mark scheme, I think, just asks you to explain that the partition coefficient was the ratio of the concentration of the solute in each of the two solvents. So those two phases there. Okay, now we've got an insecticide, or pesticide is it? The two phases are hexane and water. And initially we're going to put 0.420042 grams of the pesticide in water, and then we're going to add this other phase on top. And so what's going to happen is the pesticide will have some of its molecules will be in the hexane, some of its molecules will be in the water. And we've got to calculate the mass of pesticide that's going to be in the hexane phase at equilibrium. So, okay, so what I did for this was I said that you've got this equilibrium being set up, haven't you? And I've set up a little equilibrium table. If you remember the equilibrium tables, I for initial, C is the change, E is equilibrium. Now initially you've got 0.42 grams dissolved in 25 centimeters cubed of water. If you work that out, you've got 0.42 grams in 25 centimeters cubed of water. That works out as 1.68 grams per decimeters cubed. Okay, so initially, my mistake. It's 0.168 grams per decimeter cubed is the concentration of the pesticide in water. So initially, the concentration of the pesticide is 0.1608 grams per decimeter cubed. And initially, there's none of it in the hexane. Right? And then when you add the hexane, the molecules get distributed between the two phases. And so there's going to be a change of some of it will go into the hexane and some of it will leave the water. I've just put the amount as alpha. That's what you do in these equilibrium tables. You generally put the amount that changes as alpha. And so at equilibrium, there's alpha in the hexane and there's 0.168 minus alpha that's in the water. And so you know that the equilibrium constant is the concentration in the hexane, which is alpha, and the concentration in the water, which is 0.168 minus alpha. And so you can then do the calculation that okay, so the partition, we know that K is equal to 6, don't we? So you can rearrange that equation so that you've got 6 times 0.168 minus alpha equals alpha. I've just multiplied up. And then if you multiply that through, you find that you end up with, multiply that through is 1 is minus 6 alpha equals alpha. So alpha, 7 alpha equals 1. And then the alpha equals 1/7. If you work that out, it's 0.143 grams per decimeter cubed. So we worked out the concentration of the pesticide in the hexane. And if you know that concentration is 1.43 grams per decimeter cubed, you want to know what it is in 25 centimeters cubed. So you've got to divide it by 1,000 and multiply by 25, and you end up with a result of 3.6 times 10 to the minus 3 grams. Okay, I just wanted to focus on that work on partition coefficient, because that's something which doesn't get covered very often in A-level exams. You had to know that you had this equilibrium set up between the two phases, and the equilibrium constant was the concentration in one phase over the concentration in the other phase. You could work out those concentrations. You could work out what the amounts or the concentrations were at equilibrium, and you can multiply up to work out the equilibrium concentration of hexane. And once you know the equilibrium concentration, then you can divide by 1,000 and multiply by 25 to give you the actual mass of the pesticide that's going to be in hexane at equilibrium. Good, and that's as far as I wanted to go with all of that. I think the rest is pretty clear from the mark scheme. We haven't been able to go through everything in this masterclass this evening. And the thing is, there's a Slack channel set up for all the chemistry coaches associated with this masterclass. And so if you do have questions about the questions that we didn't go through, because we didn't have time today, then we'll be very happy to go through those in the Slack channel to cover any questions that you have about some of the questions that we didn't cover during the masterclass. So thank you for listening to the video, and wish you every success in your chemistry studies. And if you do have questions on anything that we've been through in this masterclass, or anything that we didn't have time to go through, then follow up with the coaches in the Slack channel. Thanks for listening, and I wish you every success in your chemistry studies.